Hey, it's 8 o'clock, so it's time to get started. So, welcome back. Um, the exams are not, I didn't bring the exams today. I'm going to bring them on Wednesday. So, on Wednesday, you're going to see your exam and your grade. Um, but today, we are going to start with a new topic. And before we get started, if there's any questions you might want me to answer before we get started. So this is going to be the material for the third exam. Remember that if you have the option to take the final, so if you do well and you're satisfied with your grade by the end of after the third exam, then you don't have to take the final. But the final, for those of you who might want to improve your grade, the final can help you do that. Okay, so if you have still the details are specified in the syllabus, so you can look at the syllabus and you'll see all the details how the weight of each exam is going to change if you decide to take a final.
With the final exam, would it only have the material that was on these exams, or is it everything on the exams plus everything?
The material, that's a very clever question.
So much information.
Yes. So I can answer that question two ways. That the material is gonna of the final will include everything we have discussed during the semester. But when I test you in the exams, I basically test the most important concepts. So you should expect something. I mean, I'll be testing the same concepts on the final. That kind of makes sense.
Kind of.
Yeah. So I'm not saying that. What I'm saying is when I design the exams during the semester, I'm testing the most important points for the material covered on that period. So those should be the same concepts that are tested on the final. Okay. Any other questions? Okay. So we're gonna start today with some new models for designing some of the material handling systems that we talked about on our previous lecture, and specifically we're going to focus on the conveyor models. The material that we're going to cover today is part of your textbook section 10.8. So if you want to look at the textbook, there's where you can find the concepts that we're going to be covering today. And this material is part of the first objective for this course, so develop an understanding of principles of facility location, layout, and material handling systems, and to practice the designing facilities. Okay, so I split this lecture in two parts. First part is the second bullet, the trolley and similar conveyors with discrete carriers. We're going to talk about the first type of design in which we consider conveyor loops with deterministic loading and unloading sequences. This means that we know specifically how many units we're going to be loading and unloading for a conveyor. On the second bullet there, you see that conveyor loop with Poisson arrivals. That means that you're going to have some uncertainty in terms of how many units you can load and unload in these conveyors. So today you're going to cover the first case, and then on the second part of the lecture, might come on Wednesday, you're going to look at the Poisson arrivals and also the horsepower calculations. Okay, so the objectives for this lecture: learn models for specific type of conveyors and understand the basic procedures for calculating horsepower requirements for power belt and roller conveyors. Okay, so let's start with the material. So as an introduction, we talk about different type of material handling systems. Again, we are focusing on one of them right now, which are the conveyors. And these conveyors are part of the fixed path material handling systems. And these are the most widely used material handling systems in industry. They include material handling equipment such as power belt, and roller conveyors, the trolley conveyors, and the automated guided vehicles. So specifically, we're going to look at one of them today. So the models we present in this lecture provide some basic procedures for design or analysis of various types of conveyors. So I'm showing two of them right here. We talk about some of the different types of conveyors early this semester. So I'm assuming that you're familiar with the names and the differences between them. So we're going to be focusing on this fixed path material handling system. So these are the material handling system that you know the route, you know where they're going to stop, and so on. So for the models that we're going to discuss today, we're going to focus on trolley or similar conveyors with discrete carriers. I think I have some pictures here. So these are the type of conveyors that we're going to look at. So we're going to have some cars moving around, and those cars will have a specific capacity. And you'll put your items on those cars, and those cars are going to be moving those items to the next station. So we present two types of models for conveyors with discrete carriers, such as trolley conveyors. And the first model is a deterministic model. Okay, so you know how many units are you going to be placing in this unit or these carriers every time that they cross one of the stations. That's what this means. Okay, so in reality that might be true. You might know beforehand how many units you need to put in each conveyor or in each car when you are trying to set up your production schedule. But there will be cases in which you might not know what will be the specific number of items that you're going to be placing in these conveyors. So there's some uncertainty in your demand. So focus on the analysis of closed loop unidirectional recirculating conveyors with discrete space carriers. So that will be the focus on the models that we're going to discuss today. Okay, so these are closed loop unidirectional recirculating conveyors with discrete space carrier. And that last word right there, discretely spaced carriers, means that you know that these parts will have certain capacity. Once you design the conveyor, this will have discrete capacity. So you can only accommodate certain number of items in each car. So this conveyor analysis that we're going to discuss today was developed because a number of operating problems that occur with trolley conveyors. And I'm highlighting two of them in this slide. So the first one, at the loading station, no empty carriers were available when a loading operation was to be performed. And at the unloading station, no loaded carriers were available when an unloading operation was to be performed. Okay, so this was the reason that these models were developed. So in manufacturing setting, you notice that you were trying to load your items into these conveyors. There were no carriers available to do that, so there were some problems in terms of the capacity or maybe the number of cars that you were using in these conveyors. Same thing happening at the unloading station. You were trying to unload some of the items, but there were no cars with items to unload. So the problem here is to determine what will be the right capacity for your car. So if you have a conveyor, you have some carriers, you want to know how many units you should fit in each car so you can have your production running or your manufacturing setting running in steady state. So conveyors provide many of the links among more workstations or work areas in modern production and distribution systems. Some conveyors are used basically as a transport system. Some of them are used for storage or accumulation purposes. While others support the transport or both things, the transportation and storage functions. And as we discussed last week, there's other type of conveyors such as the sortation, are also used a lot in companies that move packages or mail, such as Amazon, Barnes & Noble, and so on. Okay, so there are three principles that we need to consider when we are designing these unidirectional type of conveyors. So we're going to discuss those three. Before we get to that, we need to discuss what is the major components of a system called a conveyor. So we have three major components for this system. The first one is the conveyor equipment. The second one is the loading and unloading stations. And the third one is the operating discipline, computer control employee. So you're going to have the stations, which you're going to be interacting with the actual equipment, the conveyor itself. And also you need a controller. It could be a computer or any other type of device that will control the movement of the conveyor. So the system design parameters include equipment parameters, such as the speed of the conveyor, also the waiting space allowances for incoming or outgoing loads. So waiting space allowances for incoming or outgoing loads. And finally, the number, spacing, and sequencing. So the number, spacing, and sequencing of loading and unloading stations around the conveyor. Okay, so these are the three system parameters. Equipment, waiting space, allowance for incoming and for outgoing loads, the number, spacing, and sequencing of loading and unloading stations around the conveyor. And now we can discuss the principles used in designing these unidirectional closed loop conveyors. So the first one is the uniformity principle, which means that materials should be uniformly distributed over the conveyor. The second principle is the capacity principle, which means that the carrying capacity of the conveyor must be greater than or equal to the system throughput requirements. So your design is going to be based on the throughput requirement of the system. And number three is the speed principle. Okay, so depending on the speed of the conveyor, then you might be able to reach some of the cars or not. So the speed of the conveyor, measuring the number of carriers passing by a fixed point per unit time, must be within the permissible range defined by loading and unloading station requirements and the technological capacity of the conveyor. Okay, so these are the things that we need to consider when we are designing a conveyor. Again, we are focusing on unidirectional closed-loop conveyors. We know that the materials must be uniformly distributed. There's a capacity requirement that needs to be designed based on the throughput of the system, and also there's a speed principle that is gonna measure. It's gonna be measured focusing on specific station and the times that the cart goes through that station during the production schedule. So now we can go into the math, and we are going to try to design a conveyor, unidirectional, closed loop conveyor. And specifically what we're trying to determine is, we know the number of cars, we know the number of stations that we're going to be serving. We want to determine what should be the capacity of the cars. Okay, so the size of these cars. So here's what we are talking about. We have this figure here representing the type of conveyor that we are trying to address. So each of those circles represent a station in which a loading or unloading of items can happen. Okay, so in this case we have from 1 to X stations, so that means we can have any number of stations in this closed loop. So in red we have the stations, the workstations. And again, this is where the loading and unloading of items are going to happen. And then that line or close or loop inside those stations, let me change the color, is what represents the conveyor. And inside the conveyors, we have some dots, which actually represents the cars. So each dot represents a car, in which you can place units when you're moving, let's say 4, you can put or load or unload something from this station, then this car is going to move to the next station and so on. So each dot represents a car. Okay, so remember that what we are trying to, a type of conveyor that we are trying to address here is something like this. Okay, in which you're going to have cars or something like this that are moving, and you're going to be loading and unloading items to those cars. Okay, so these are some additional description here. So there are S stations located around the conveyor, numbered in reverse sequence to the rotation of the conveyor. Each station can perform loading and or unloading. There are K carriers equally spaced around the conveyor. And the passage of a carrier by a workstation establishes the increment of time used to define the material loading and unloading sequences. Okay, so we need to have a station used as a reference point to determine the number of cycles that each car is going to make. So station 1 is used as a reference point in defining the time. Consequently, carrier N becomes carrier N plus K after passing station 1. Meaning that if you have 9 carriers, let's say you have 9 and you're using 1 as your reference point, this car will be car 1, but when you cross that station one more time, then if you have 9 carriers, that car will become car number 10 because it already passed that station once. So the sequence of points in time at which a carrier passes station 1 is denoted by Tn, where Tn is the time at which carrier N passed station 1. The amount of material or number of items loaded on carrier N at its pass station I is given by F. So Tn, we have Fin, and that's for each of the stations. So I1 to S is the number of stations, and the amount of material carried by carrier N immediately after passing station I is denoted by these parameters. So this is HIN. Okay, so this is gonna get a little bit complicated now because we're gonna use those parameters to find some model. Okay, so each carrier may hold multiple items, and again, our goal is to determine how many items should be allowed to each carrier to move. So for steady state operation, the total amount of material load on the conveyor must equal the total amount of material unloaded. So at the end of the production, you don't want to have items moving by themselves in the conveyor. You want to be able to get them out of the system so you can move to the next production schedule. So since it is assumed that the conveyor will be operated over an infinite period of time, the sequences that we defined in our previous slide, Fin, are assumed to be periodic with a period p. Thus, we have the following relations. So we have for each station and for f of each station of the carrier number equals the same parameter plus the time period. So, and also if we sum all those values, then at the end, if you want to have a steady state operation, total amount loaded and unloaded must be the same. So when you add those items, the relationship should be equal to 0. Okay, so in analyzing the conveyor, it is convenient to employ the following relationship, and you're going to see how this is applied with the example. So we're going to look at the summation of all the FIs for each one of the stations, and we can obtain the following result. So for these models, when you divide the number of cars by the number of periods, this cannot be an integer value if you want to reach steady state operation. Also, we're going to have a new parameter R that is going to be equal to K mod P. And I'm going to show you what that means in a second. In that relationship, when you look at this division, must be a proper fraction for these models to work. And finally, it's not forced, but it's helpful to have a prime number for your period. Okay, so going back to this operator, are you familiar with the mod operator? MOD, what that means? So you basically are trying to find the residual value of a division. So if you do here, so we are looking at the remainder following the division of K by P. So for example, if I do 12 mod 7, that a reminder for that division, which is is 5. So 7 mod 12 mod 7 equals 5. Is that residual value when you do the division? So 7 divided by 12 divided by 7, that's 1, 7, this is 5. This is the value. That's what that operator gives you, the mod operator. Yes, sir.
So, in that example we're in, the example the one would not matter or whatever, we have to value this stuff.
Say that again, the value of
For
4.
example, if we had 4 divided by 5,
Mm-hmm.
it would still only be 1.
Yes, yeah, it will be 1. That's correct. And you can get the same value for different type of numbers or different numbers. Yes, that's correct. Any other questions? Okay, and another example, if we do 26 mod 8, that equals 2. Because 8 times 3 is 24, and you're going to have 2. Okay, so what we are going to do now is to go through the equations that you're going to need for determining the capacity of each one of these carriers. And these are recursive equations. So if you have taken any courses like dynamic programming or anything related to that, this is the type of equations that we're going to use. If you haven't taken those courses, don't worry. I'm going to go through the steps, and we're going to practice this with the lab today. So here are the equations. The material balance equation for carrier N can be given as follows. So go back here. So HIN is, see if I can keep this here. Amount of material carried by courier N after passing station I. Station I or N? Yes, I. Okay, so what we're trying to do here is we're going to look at production time, you know, 3 times per year, and we're trying to determine the steady state of that system, and we are going to determine how many cars do we need, so we can move the items that we need in steady state for our system. Okay, so you're going to be dealing with time and also with a certain number of carriers for our design. Okay, so materials balance equation. So we're going to look at the value for each carrier, and for the first station that we're going to use as a reference, we can determine the amount of material carried by any car after passing by station 1 using this relationship. Okay, so in order to determine the values of HIN, we need to look at this recursive formula or recursion. So what we are trying to do is kind of solve the problem backwards. So we're going to use the values from the previous period or car to determine the values of the next car. And letting H start 1 in your particular solution to the equation 1, and using this recursive relationship, we can solve this first equation. So we're going to start by letting H1 start equals 0, because we're going to start with something. And then using that value, we can start solving for the next cycles and for the cars. So this is our next recursive function. So given HIN, the value of HI plus 1n is obtained using the value of HI star n minus the value of f. So going back here, we also put here what that f means. So FIN is the number of units that you're going to be loading. Okay, so these are the units that you're going to load into the carrier when you pass station I. This is the amount of material that is carried by that car after passing the station. Okay, so you're going to add, you're going to subtract, and then HI is going to give you, so after you're adding or subtracting, this is the amount of material that you have. Okay, so once we determine those HI values, then we are going to find this parameter C, which is going to be the minimum of the HI stars, and then the desired solution in terms of H is given using the H1n minus Z. And finally, we can find the required capacity per career by looking at the maximum of those HI and values. And this is going to make more sense with the example. So again, we're going to go through these steps, and the idea is to find what will be the required capacity for each one of the cars that we have available in this conveyor based on the loading and unloading requirements for our production. Okay, so we're going to be putting and subtracting some of those items from each car as the production moves in time. So let's try to go over this example. So to illustrate the deterministic solution procedure, consider a situation involving a single loading and a single unloading station. So instead of having multiple, like 9 or 10 stations, we are going to focus on a very simple example. We only have 2 stations, which are depicted here, 1 and 2. One is going to be doing the loading, and the other one is going to be doing the unloading. Okay, so the tasks for each station are very specific. The conveyor that we are looking at has 9 carriers. Okay, so we're going to have 9 cars moving around. And those 9 cars are the ones that are going to be loaded and unloaded. They are equally spaced. And we want to determine the required capacity per carrier. The loading and unloading sequences occur with period of P equals 7 and are given here. So the first car that passed through station 1 is going to be loaded with 1 unit. Second car is going to be loaded with 1. Third car is going to be loaded with 2. Fourth car is going to be loaded with 2. Fifth, and so on until you get to 7. At that point, the sequence for loading is going to start over. So car number 8 is going to be loaded with 1 unit. 9 is going to be loaded with 1 unit. 10 is going to be loaded with 2, and so on. So this period of loading sequence is repeated after 7. Okay, so first 7, this is the sequence, then 8 is going to start here, 9, 10, so on, then start over again. Same thing for the unloading sequence. So the first car, 0, 0, 0, 0, first, second, 0, third, until you get to 6, you're going to unload 5, 7 is going to unload 5, then 8, you're going to unload 0, and so on. What else? So that's the information we have. So let's try to go over the steps. So the first thing we have to determine is if one of n, and going back here, is that summation of i's are the stations. So you're going to look for each period. You're going to add for each period the loading for each one of the stations. So we only have 2 stations. So we're going to add for each period the loading and the unloading. So for the first period, we're gonna add 1 plus, gonna be 1 plus 0. So here, so that's 1. For the second period, it's 1 plus 0, so that's 1. Third period is 2, so this is 1 plus 0. 2 plus 0, so that's 2. Then 2 plus 0, that's 2. 2 plus 0 again. And then you get to 1 plus minus 5, that's minus 4. And then 1 plus minus 5, that's minus 4. So those are our f values. And they're coming from here. So you're adding for each one of the time periods the f values. So 1 plus 0, 1 plus 0, and so on. Okay. And we can determine R using the mod operator. So K mod P is going to be equal to 9 mod 7, which is going to be equal to 2. So R equals 2. And going through the bullets that we discussed earlier to check on if we can apply this model or not, we need to check if this is not an integer, so K divided by P. R divided by P is a proper fraction, and P equals 7, which is a prime number. Okay. So now we can move to determine these values after each car passed the station. How many units will it have? So recall that the amount of material carried by carrier N immediately after passing station I is denoted by HI10. So we need to start with something. The model basically what it does is it assumes that the first carrier will start with 0, and then it's going to use that as the first as seed value. And we're going to employ the relation H1 star equals H1 star n minus R plus Fin, which is coming from the recursive relation that we discussed earlier. Okay, so using H, we put here, it should be H star 1 equals 0. So if we know this number, then that's providing us with this value right here. So we can determine this one. Why is that? We just found that R equals 2, right? So if we plug 2 here, the only value that will give us H of 1 is going to be R n equals 3. So going back here, just determine that R equals 2. we are trying to use the recursive equation to find the amount of material carrier by each one of the cars in this conveyor after passing a specific station. So we start by allowing the first car to be 0, and we can use this to find the next car, the amount of units that are carried by the next car passing by the same station. So if we tree equals HR star n minus R. So if n equals 3, R equals 2, then we get F. So we can determine the next one that we can determine is the value of the third car passing by station 1, because we know that H1 of 1 equals 0, and R equals 2, so that value right here is this value that we assume. Okay? So that's what we're going to see on the next slide. So since we arbitrarily let HI, it should be 1, equals 0, and employ the relation H1 star n equals H1 star n minus R plus F1 n, to determine H1 star, we do the following. So H1 star 3 equals H1 star 1 plus F of 1, 3. We know that H1 star of 1 equals 0, and we can find F of 1 of the third car, from the first thing we did for the example, which was to determine the values of F. So if we go back here for 3, that value equals 2. So this is 0 plus 2, and this equals 2. Likewise, we can, now that we know H1 of 3, we can determine H1 of 5, because again, R equals 2, so we can move 2 H1 star 2. So this equals H1 star of 3 plus F of 1, 5. And that is 2, which is coming from here, plus 2. And that is 4. And again, since R equals 2, this computation is going to be for H1, 7. So H1 star 7 equals H1 star of 5 plus F of 1, 7. And that is 4, which is coming from here, minus 4, which is coming from the F values. Yes, sir. Yes. Okay. Okay, so we start like assuming that the first car is going to be empty. First car passing through station 1 is going to be empty, have no items. Okay, so that's our first assumption. So using that value, we can find the number of items that the car n plus 2, I'm sorry, n minus r units or n minus r order. Let me go back here. Okay, so this R value is very important because this is what's going to allow us to know what's the next car that we are going to find in our sequence. What is the next car that we are going to look at? Okay? And we are going back to this relation here. So in order to solve this equation, we need to start with something. And that's why we are assuming that H1 of 1 is going to be 0. That's going to give us something to get started. But if you plug that here, okay, if you plug H1 of 1 here, that means that you need to look at you're solving for the car that has the value n minus r. And the only value that will satisfy this n minus r equals 1 is going to be 3. Okay, so that's why we move to 3 here. Okay, and we find for 3, we're going to use the initial value of 1, which is 0. So that's why we have 0 here. And f of 1 of 3 is coming from here. So we got 1, 2, 3, value is 2. So we have 0 plus 2. Likewise, go back to same equation here. Now we know the value of 3, and the only number that will satisfy n minus r equals 3 is going to be 5. So that's why we are solving for 5. And we use the value of h1 star 3, which is here, which is 2, and we're going to add the value of f1 5. 1, 2, 3, 4, 5, which is 2. And that's where we get 2 plus 2 equals 4. And then we repeat the process. You're looking at car number 7. We know the value of 5, which is 4. And f of 1 of 7 is minus 4. Okay? So that's where we got up to there. Okay. But remember that the loading and unloading sequence or period has 7 items, and that sequence or period is going to be repeated once you get to item number 8. Okay, so 7. Now we need to determine what's going to happen with our 9 carrier. So H1 star 9 is obtained. However, since P equals 7, H1 of 9 is going to be equal to H1 of 2. Why is that? Because that sequence or the loading and unloading is going to be repeated. So this H1 star 9 is going to be equal to H1 star of 2. And H1 1 start is going to be equal to H1 start of 7. I'm going to delete this so you don't get confused. This is already here, so I'm going to take this out of here. So H1 start of 9 is equal to H1 start of 2, which is going to be equal to H1 start of 7 plus F1 2. And this is 0 plus 1. And this equals 1. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. These are the cars. We have 9 cars. And then we have the loading sequence. Here is 1, 1, 1, 2, 1, 1. So what you need to see here is that we have a loading sequence that is shorter than the number of cars that you have. Meaning that at this point you still have a couple of cars that you need to load or don't load. So what's going to happen is you're going to repeat this sequence again. So that's what this is telling. This loading and no loading sequence is going to be repeated. After 7, you repeat it again. After 7, you repeat it again. So since you have 9 cars, then you're going to start repeating that at car number 8. Okay? And that's why we're saying that H of 9 is going to be the same as H of 2 because that sequence is repeated. Okay? So H of 1 of 9 is equal to H of 1 of 2 because when you get to 9, that's the same sequence that you observed here. And likewise, we can determine, so we have card 3, we have card 1, so let me see, we'll have 1, 3, 5, 7, we have 2, which is here. So we have 1, 2, 3, 5, 7. We have to determine for H of 1 of card number 4. So that's H of 1 start of 2 plus F of 1, 4. And that's 1 plus 2 equals 3. And so we have 4 here. And we also need H of 1 start 6, which is equal to H of 1 start 4 plus f of 1, 6. That's 3 minus 4. That's minus 1. So we have 6. Okay, so we have all the h or from 1 to 7, and you know that after that the sequence is going to be repeated, so we can find the h for any number after we determine the values from 1 to 7, and that's what we did. Okay, so using this information, we can list the values of h. So h1 star n equals 0, 1, 2, 3, 4, minus 1. And 0. Okay, so those are the values that we just found. Okay, so we have that information, and that's for the first station. Now we have to look at the values for the second station, which is H2N. And yes, sir.
So H1 is the number of materials very bottom of the negative.
Yes, and that's a very good question. We have a negative value here. That can mean two things. You're short by 1, or yes, you cannot do unloading in this station, so that means that you're short by 1 unit. And that can happen, have a negative number there. So that basically means that you're short by 1 unit. So you don't have enough to, you're supposed to do this many and you don't have enough to put there. Okay? Yes, exactly. And that's what we're trying to determine. So these are the loading and unloading sequences. Maybe the size of the car is not rightly designed, so we are trying to find what's the best size of the capacity so we can have a steady state and that avoid those things. Well, that's a very good question. So now we're going to look at the number 2, station number 2. And in order to get the values for h here, we're going to use this recursive equation. So h2 star n is going to be equal to the values of h1 star n, which is 0, 1, 2, 3, 4, minus 1, and 0, minus the values of f1n, and we know those are coming from here, f1n. So these are 1, 1, 2, 2, 2, 1, 1. So h2n equals minus 1, 0, 0, 1, minus 2, and minus 1. So again, now you're seeing other negative values here. And in this station, you can actually do unloading. So you're going to have some minus negative numbers there. So the value of z is bound to be, again we're going back here, c is going to be the minimum of all the h for all the cars. So we're going to look at H1 and H2. And we're going to find the minimum. So H1 is here. The minimum value here is -1. H2 is here. The minimum value here is -2. So Z, again, is going to be the minimum. So in that case, from all the H, let me put it here. This is the minimum I n H I star n, and that's -2. So we are looking at these values and these values, and that minimum amount is here. Yes, sir. That's for H2. Oh yeah, yeah. Sorry. Let's see. It's -1, 0, 0, 1. There should be a 2 here. Yeah. Thank you. Okay. So we got to this point. We're almost done. I don't think we're gonna have the time to do the lab today, so we're gonna do that on our next lecture. So for I equals 2 and n equals 6, the sequences h, I, n are given by h, I, n equals 2, 3, 4, 5, 6, 1, 2, and h2 n is 1, 2, 2, 3, 4, 0, and 1. And this is yes. We're gonna go here. So this is coming from here. Okay, so we are subtracting z. So this is gonna be -2, the value of each h. So for example, let's do the h1. It's gonna be h1 1. It's gonna be 0 -2. That's 2. So that's what we got. So let me put that here. So you obtain these numbers using h, I, n equals h, I star n minus c. And finally, b is going to be equal to the max of I n, h, I, n. So we're gonna look at the maximum number from these two guys here, and that maximum number is 6. And that happens for I equals 1 and n equals 5. So therefore, each carrier must have sufficient capacity to accommodate 6 items. And we did all that process to get to this. Okay? So we're going to repeat this exercise on Wednesday. The only thing that I'm going to change is the number of cars. And you'll see how the analysis will be changing and how the capacity at the end will also be different. Okay? So that's all I have for today. On Wednesday, we're going to go over this one more time. We're going to go do the lab. And also we're going to discuss the exam. And I'm going to give you the grades on Wednesday. Any questions? Okay, so I'll see you on Wednesday. Thank you, sir. Just 1 second.